terms of information elements, packaging, and composition in vertical services for the transport and logistic area. And finally, I will give some hints on the experimental tools that we are enabling in our VITAL-5G platform for the validation of NetApps and vertical services. So just a brief overview of the project. What we are going to propose is basically a 5G-enabled platform for the validation of transport and logistics services composed of multiple NetApps that can be developed and composed together from multiple stakeholders. And our main focus here is basically to facilitate the adoption of the 5G technologies in the areas of transport and logistics. Basically trying to engage several stakeholders coming from the vertical industries in the 5G environment. So simplifying somehow the adoption of the 5G technologies and the modeling of the 5G capabilities in order to simplify their integration in the NetApps and in general in the services that can run on top of 5G infrastructures. In order to do this, we offer a wide set of tools and facilities to automatically test and validate the performance and the capabilities of the NetApps in a 5G environments, considering different types of KPIs that can be related to the network itself, but also to the service performance. So our platform integrates several components. In particular, we have 3 different 5G testbeds. 2 of them are related to ports. In particular, we have a seaport and a river port, and a logistic sector. Then we have the transport and logistic infrastructures that are extended to integrate the 5G facilities and technologies. And we have the concept of NetApps. NetApps that can be developed and proposed by different stakeholders, software developers, vertical industries, and so on, and can be onboarded in our catalog so that they can be made available for other actors in the market. We offer also an experimentation platform that facilitates the validation and the performance evaluation of our NetApps. And finally, we are engaging with several stakeholders, including also third parties, so going beyond the actors initially included in our project. This is the overview of the architecture of the VITAL-5G system, where you can see the 3 different facilities, in particular the seaport in Antwerp, the river port in Galaţi, and the warehouse in Athens, that are extended with the 5G infrastructure. Our target is to reach the deployment of the 3GPP release 16 standalone mode in all the 3 testbeds. And on top of everything, we have developed our experimentation platform with an open online repository of NetApps and vertical services in the transport and logistics sector. The final objective is to enable trials of transport and logistics services to evaluate their performance in different contexts and in different environments in order to facilitate their potential commercialization in the market. In this sense, we plan to involve several third-party experimenters that will be able to reuse the NetApps coming from our own catalog, but also to propose and to onboard their own proprietary NetApps. And the composition and combination of these NetApps can generate new services that can be tested and validated in our environment in order to facilitate, simplify, and speed up their commercialization. In our roadmap, we have just released our early drop at the end of March with the first set of tools for NetApps validation and experimental results analysis. The plan is to have other 2 releases in month 23, then at the end of the project, increasing the capabilities of our system, but increasing also the portfolio of our NetApps. So what is a NetApps in VITAL-5G? Basically, for us, a NetApp is a virtual application that exploits the 5G capabilities. So it's a 5G-enabled application that is able, of course, to provide its own set of functionalities when deployed as a standalone entity, but that is also able to cooperate and interact with other NetApps to deliver more complex transport and logistics services. These NetApps, of course, can come from different actors, different application developers. So in this sense, NetApp is somehow extending the traditional concept of virtual network function, or even the cloud native network function, declaring some additional characteristics that on one hand cover the nature of the 5G enabled NetApp, so basically define the connectivity requirements in terms of mobile network. For example, explaining the kind of 5G slice profile that is required to run and to access the NetApp itself, or, for example, the 5G core services that can be consumed by the NetApp in order to provide added value services. For example, the consumption of the localization service provided by the 5G network, or the consumption of the network analytics service, again, provided by the 5G network. On the other hand, our target is to facilitate somehow the definition of the NetApps, trying to speak the same language of the verticals and of the application developers. So in this sense, we are proposing an information model that simplifies the definition of the NetApp itself, but also their composition in end-to-end vertical services and their reusage or sharing across multiple services. In a complementary way, we are also defining a set of tools and also developing a set of tools that facilitate this definition of NetApps, the creation of new NetApp and their distribution in our catalog. So, for example, we have defined the NetApp packages and the NetApp blueprints that I will describe later on. We have a NetApp catalog in our VITAL-5G open online repository that allows to onboard new NetApps from third parties, but also to browse and discover the NetApps that are already available in our own catalog and provided as part of our project results. We have a number of validation tools that are used basically to verify the modeling of the NetApps, the performances of the NetApps in a given target environment. And this declaration can also be supported through an intent-based interface or some wizards that allows to simplify all the procedure for the declaration of the experiments, the definition of the metrics and the KPIs to be evaluated, and the test cases that we want to use to automate the validation process. So NetApps, the categorization of NetApps, at least in our case. NetApps can be application specific or application agnostic. So an application specific NetApp is basically addressing specific industrial challenges for the transport and logistics sector, and they are usually bound to the specific characteristics of the environment where they must be deployed. So, for example, the autonomous or the remote vessel control needs to interact directly with vessel interfaces. And for this reason, it must be a specific NetApp. Similarly, a human-robot collaboration application needs again to consume the APIs that are specifically exposed by the robots. And again, in this case, they must be developed specifically with the testing environment in mind. On the other hand, we have other application agnostic NetApps that can be suitable for different contexts and can be reused in a variety of vertical applications and transport and logistics services. Examples are an IoT management platform capable to interact with different field buses, or an application for data ingestion, data fusion, data processing, and so on. So these are more generic NetApps that can be reused in different contexts and can be combined together in order to deliver new service. As you can see, the chaining of multiple NetApps that could be both specific and agnostic ones gives the so-called end-to-end transport and logistic service, where basically the functionalities of the end-to-end service are given by the combination and joint cooperation of the various NetApps that are composing the service itself. In this sense, it is fundamental to enhance somehow the definition of the NetApps with all the information that simplify the composition of the NetApps in an end-to-end service. In this case, it's critical to clearly describe the interfaces that are provided by each NetApp, and at the same time, the interfaces that must be consumed by other NetApps. This approach allows to identify clearly, starting from the catalog of the NetApps, how different NetApps can be plugged together into the end-to-end service. This allows the developers and the service providers to select from the VITAL-5G catalog the specific NetApps and to combine them together to deliver the network service and also new network services. New network services that can be also customized as needed for the business, the specific business of the verticals. In order to do this, we adopt the concept of the vertical service blueprints that basically provides a number of variable service parameters, again speaking the same language of the verticals, or not specifically oriented to the network capabilities and the network definition. And such blueprints are internally interconnected to some network service descriptors that on the other hand includes the references to the specific virtual network function or cloud network functions, and that are defining how the service itself should be deployed on top of a virtual infrastructure. Starting from this vertical service blueprint, it is possible to customize the service, declaring the specific values of the variable service parameters. This procedure originates the vertical service descriptor that can be provided by the user in order to trigger the creation and the instantiation of the service. So starting from these service-oriented variables, the system performs internally all the translations that are required to derive the specific network service instance that at the end is composed by different NetApps to instantiate these virtual components in the virtual infrastructure, and at the same time, based on the high-level definition of the network capabilities and requirements defined in the blueprint, to select and instantiate and provision the network slices on the 5G network that are required to guarantee the specific quality of service required by the various NetApps. So in terms of modeling, as I've mentioned, we have defined the NetApp package that, as you can see, includes partially the virtual network function package that could also be container-based network function, so include the CNF package instead. Of of course, all the software images, and these are basically defining how the NetApp should be deployed in the virtual infrastructure. But together with that, we are extending the package, defining the so-called NetApp blueprint. NetApp blueprint is the one that provides the metadata that are used to identify the specific features of the NetApp, the structure of the NetApp following a service-oriented approach, so basically identifying the components of the NetApp, the endpoints of each components, how such components should be interconnected, and which kind of interfaces are exposed by all these components. At the same time, we have the requirements in terms of 5G network. So, for example, the kind of slice profile and service profile that is required in terms of latency, of throughput, of jitter, and so on. The kind of KPIs that should be monitored and potentially should be used to automate the lifecycle management of the service and of the single NetApps, for example, related to the scaling of the system. And finally, since we are working in a transport and logistic sector, it's important to consider the compatibility with the hardware. So the fact that, for example, an NetApp is interacting with a given vessel, is interacting with a given AGV or robot or whatever. This is the information model that we have defined in the project. Of course, I'm not going into the details of the single elements here. If you are interested, everything is defined in our deliverables that are available, publicly available on our website. The important point here is to highlight that everything is embedded basically as part of the NetApp package in the different elements of the VNF package, for example, of the VNF descriptor, in specific license files that are related to the software licenses of the NetApp software within the NetApp blueprint, or as additional files, again, in the NetApp package that are, for example, related to the software documentation or to the testing and validation specifications. These are, of course, useful for the software developer in order to combine and reuse the NetApps from our own catalog. This is basically the representation of how the different elements are encoded in the NetApp package. And the focus now is more on the NetApp blueprint that is defined in the JSON format and includes a lot of information elements that you can see as represented here. Here I would like just to focus a bit more on the 5G capabilities. For example, the definition of the slice profile associated to the endpoints that are interconnected, for example, to the RAN of the 5G infrastructure. In this case, we can give the details of the EMBB slice profile or the URLC slice profile, depending on the specific type of NetApps. So if it's required mobile broadband capabilities or ultra reliable and low latency capability. In terms of infrastructure metrics, we have a number of metrics already defined in the project, and this kind of metrics can be extracted automatically from our testbeds. For example, in terms of network API, we have the user data rating, downlink and in-app link, the latency at the user plane and the control plane, the round trip time, the reliability and the availability. Of course, we are considering also the infrastructure capabilities in terms of computing resources. So, for example, the usage of the CPU, of the memory, of the disk, and so on. And all these metrics can be collected dynamically and can also be accessible for the NetApp itself. The full specification of the NetApp blueprint, again, is available in our deliverable, and there are also a couple of examples of specific blueprints that can be used in order to develop new NetApps. This is just an example of vertical service. In this case, it's a vertical service composed by 3 different NetApps that are interconnected together. One of them, as you can see, the IoT management platform, is collecting data from local IoT supervisor that is interconnected using the 5G infrastructure. If we move to focus on one of these NetApps, we can say that the modeling of the internal details of the NetApps are completely agnostic, let's say, from the 5G infrastructure itself. So we have basically the definition of the service components, the definition of their endpoints, how they are interconnected together, and in case of NetApps that are actually interconnected to the 5G network, we have the definition of the 5G service profile. This definition is basically defining simply the characteristics of the mobile connectivity that is required from the perspective of the NetApp. But as you can see, it doesn't give any detail about how this kind of connectivity should be provided in terms of 5G infrastructure. Similarly, we have the modeling of the hardware dependency. So, for example, in this particular case, we would have the dependency on an IoT gateway that is deployed on field and allows to collect the data that can be extracted from the various sensors or to command the various IoT actuators that are deployed in the vessel, in the warehouse, or wherever is the target of our NetApp. We have developed a number of NetApps in the project. This is the complete set. In the early drop at the end of March, we have released 4 particular NetApps, 2 vertical agnostic and 2 vertical specific. Some of them are open source, so here you have the link to the GitLab repo in case you are interested in that. During this webinar today, we will show a couple of them as concrete examples. So to basically conclude the presentation, I would like also to give you an hint on the capabilities of our system. Basically, we provide services for different kinds of actors, both internal or third parties. These actors can be NetApp developers, transport and logistic verticals, service provider, experimenters. All of them can access our system from a single access point that is the VITAL-5G platform using our portal. And then the VITAL-5G platform will basically mediate all the interactions with the 3 different testbeds. This is the procedures for the experimental validation of services based on NetApps. Our system is basically supporting all these different phases with a number of tools that can be used at the different stages. So, for example, in terms of service design, we provide, of course, the catalog of our own NetApps, but there is also the possibility to define and onboard new NetApps in the system and in the catalog. There is the possibility to design the experiment, for example, to select the target testbed where you want to perform your test, the specific customization of the 5G environment if required, the kind of network and service KPIs that should be monitored, the test scripts and the variables that can be used to automate the testing and the experimentation process. We have also the possibility to deploy dynamically the vertical services. Again, this is done deploying the different virtual machine or containers that are composing the NetApps, but also creating or selecting the most suitable network slices that guarantees the performance in terms of mobile connectivity as required by the NetApp definition. We have the possibility to execute the experiment with the automated collection of the network and service KPI and the possibility to evaluate in real time if the traffic that is related to the NetApp is somehow within the boundaries that are expected in terms of 5G performance. Finally, we have also a number of tools that facilitate the automated diagnostic and the evaluation of the results basically elaborating dynamically the statistics that are collected by the system. The repository is basically where all our NetApps can be collected, onboarded, selected, and reused. We have mechanisms for the authentication and authorization. This is also to enable the simplified access to third-party users that can select the public NetApps from our catalog and compose them to deploy their own services. In terms of functionalities, we have a number of features that are extending the traditional concept that were already in place, for example, in ICT 17 project. So, for example, we have the possibility to validate automatically the blueprints of the NetApps in a target testbed before their provisioning. We have the capability to manage the licenses, the possibility to share NetApps and to reuse NetApps coming from different verticals and stakeholders into end-to-end services, and the possibility, of course, to control the access in order to regulate basically the experimental activities for concurrent services and the sharing of the resources and of NetApps also with third-party actors. This is a representation of our system. There's a portal web GUI where you can access all the tools of our platform. And of course, in case you are more interested in a programmable interfaces, you want to integrate your own systems with our platform, we also expose open APIs. This is just the example of the catalog, but the same is available for the service lifecycle management in order to enable the interoperability with third-party systems. That's all from my side.
Thanks a lot, Jada. Nina, can you please continue?
Yes, sure. Let me share my screen. Okay, I hope you see my screen now.
Yeah, everything is perfect.
Okay, thank you very much. Hello, everyone. Thanks for joining our first webinar. My name is Nina Slamnik-Kreštarec, and I am a researcher in IMEC and University of Antwerp, ID Lab Research Group. Today, I will be talking about one example of vertical specific NetApp, which is called Onboard Data Collection and Interfacing with Vessel Turcofin 2. But before talking about this particular NetApp, I would like to introduce a bit more the use case that we are developing in this project, and then later on reflecting on how this particular NetApp is playing the role in this use case. So use case on the automated vessel transport at the port of Antwerp is one of the three main use cases in VITAL-5G project. And together with other partners on the Belgian pilot site, such as Telenet, Digitrans, and CFAR, we from IMEC are developing components of the overall use case. So as in any kind of port that we could have, today 5G is playing the role now to bring the automation and to improve the operational aspect of the operations in the port. So basically to leverage 5G and artificial intelligence and different machine learning algorithms, we can basically make the port smart. And on the right-hand side here of this figure, we show one very high-level overview of how this any kind of use case that you want to deploy in the context of 5G port that could be deployed. So starting from the 5G user equipment as one of the segments of the overall 5G ecosystem in the 5G port, we of course talk about the vessels here in the port of Antwerp, and the onboard units, like any sensors that this vessel is equipped with, cameras, different GNSS devices that track the location of the vessel, and etc. All of that could be transferred to the network, basically through the network to different NetApps and vertical services running on the control center or the NetApp platform. So basically here, if 5G user equipment is available, then this kind of traffic coming from the sensors and cameras can be transferred all the way through the 5G access and 5G core to the services running on the NetApp platform. In this case, we differentiate here in the figure two main types of 5G network slices that could indeed be leveraged in the port operations. One of them is the enhanced mobile broadband or EMBB type of slice, which is shown here on the left side. And basically, this could be used for collecting the data from the environment and from the vessel directly, ensuring enough bandwidth in the upstream direction. And for the other type, which is, for example, vessel assistance, if we want to assist the navigation of the vessel remotely and to monitor the vessel, then we could indeed leverage this type of service such as vessel assistance and make use of 5G network, in particular the ultra-reliable low latency communication to send a notification to the captain who is on board, or even to navigate remotely the vessel. Of course, apart from the 5G capabilities, what else do we need to enable such use case is, of course, high bandwidth camera feeds that are on the vessel, real-time sensor data, and also we need different kinds of NetApps that will help vessel and the captain to make different kinds of decisions in the operation. So basically, this could be real-time steering command sent from the NetApp all the way to the vessel, or it can be a real-time digital twin that we develop to extend the awareness about the environment around the vessel, and of course to optimize further the route in a real-time way. Some of the challenges that I'm pretty sure every port is facing is lack of personnel and high traffic density, and this is not an exception for Port of Antwerp. In particular, if you don't know, Port of Antwerp is one of the largest ports in the world and second largest seaport in Europe. And of course, these challenges, such as lack of personnel and high traffic density, are causing large delays in port operations. And it affects not only the port operation, but in general, any other operation affected by the port. And of course, the other aspect is insufficient safety, because various accidents and unplanned events can also cause different disruptions in the operation, which not only causes the lack of safety, but also increases the delays in operation. One of the solutions that we consider in this project and that we study in particular in this use case is to leverage 5G communication to collect decentralized data from vessels and from the environment, and to basically run different kinds of processing algorithms, either rule-based or any kind of analytics or artificial intelligence on the NetApp platform to basically improve the operations and improve the safety. So to do that, of course, we studied the requirements for delivering such use case. Not only the business requirements, but also what is required from us to have on the facilities, and also very important from the network itself. Regarding business requirements, we need to improve infrastructure safety, as I already mentioned. We also need to improve in the port areas, the dwell time in the port area, which is basically caused by loading and unloading and very inefficient way of doing that operation. And also to improve very much the captain and ship planning gaps because of the very tight schedules for the operating vessels. The improvement in that regard could be indeed leveraged from the network itself and from the network applications that we develop in this project. Regarding facilities, we of course need end devices such as cameras, lidars, GPS, VHF transceivers. And we need, of course, some network function virtualization platforms that will enable us to onboard and to run those NetApps. Regarding network requirements, we've been studying here in this graph in particular how 5G or existing deployments of 4G can help us develop this use case. And in the here in the yellow part, you can see how is our VITAL-5G use case behaving in or how are the requirements placed in terms of, with reference to the 5G and 4G. 5G is the lighter blue one, and the darker blue is the 4G. So you can clearly see here that requirements for our use case on the reliability and availability are not met with 4G, and we need to improve that by using 5G and leveraging 5G to achieve at least 4 nines of reliability and availability, or 99%, 99 reliability and availability. Also for the capacity, we need to leverage 5G. And other thing that is here shown as latency, for this use case, we require lower than 22 milliseconds. But in theory, 4G could help us achieve that, but in practice, we all know that it is really hard to achieve. So we also, for the latency, that could help us to send HD camera feed uplink, but also in the remote monitoring to share the camera feeds with the captain on board, we require a lower latency than that, and also service interruption lower than 150 milliseconds for the ship control. This really helps us to see the benefit of 5G that we could indeed leverage in this use case. Based on that, we show here the pilot site that we are planning to use and demonstrate this particular use case. So the use case will be implemented and demonstrated in the real world scenario in the port of Antwerp. And here we show just one example route that could be used for the demonstration. Although it might change due to the business of the port, this arrangement need to be fixed, but of course are changeable during the lifetime of the project. But in the VITAL-5G, we indeed plan to demonstrate the help that network applications or NetApps are providing to the vessel and the captain who is on board to improve the operation of the vessel. This will be the case with the ship navigating through the Scheldt River in Antwerp, and using the help from autonomous navigation assistance and remote monitoring, where in the first case, captain will receive trajectory from our NetApps, the trajectory that he or she needs to take to optimally navigate the vessel, while in the latter case, the remote monitoring will help the captain not by sending the notifications about which route to take, but basically sharing the camera feeds of the surrounding environment to show the overall operation and to improve basically the operation of navigating through some very narrow channels. Here, just a glimpse on the 5G deployment. Here is how we deploy different antennas and base stations in the port of Antwerp. In particular, our partners from Telenet in Belgium are in charge of that, and this is what is currently available. And of course, more RAN sites will be available in the whole area to provide a larger RAN coverage. So Jada already introduced the relationship between use case, vertical services, and NetApps. And in this particular use case, we have developed 2 different services, or we designed them to basically deliver the main logic of the use case and the operation. The first one is vessel autonomous navigation assistance, and the second one is vessel remote monitoring. Both of them, I briefly described them in the previous slide when I was referring to the demonstration of the use case. But indeed, both of these services are leveraging smaller NetApps, which basically break the logic of the overall use case, and they are instead in charge of a smaller portion of the overall operation so that they could perform it in the best possible way. So from the NetApps, we have real-time digital twin, remote vessel monitoring, autonomous vessel navigation control, navigation speed optimizer, and onboard data collection and interfacing for vessel Turcofin 2. And in particular today, I will talk about NetApp VS8, which is onboard data collection. And this is how it is basically connected with the other NetApps in our use case. And as you can see, this is the NetApp that connects directly to the vessel to collect data from it through the 5G infrastructure. So from the next slide, I will be talking about this particular type of NetApp. Jada also introduced the difference between vertical specific and vertical agnostic NetApps. This one is vertical specific because this is it is designed for interfacing with vessel Turkopin 2, and for addressing this particular operation with this vessel. But of course, it could be even more generalized and then used for other vessels or for any other vehicles or AGVs or robots. The role of this NetApp here is to, of course, collect the data from the vessel. In this case, this is GNSS data on the speed, location, and heading of the vessel. And this data is then further collected through the 5G infrastructure all the way to the onboard data collection NetApp, which is running on the NetApp platform. This collected data is not used by this particular NetApp per se, but the idea is that this NetApp is leveraged by the other NetApps in our use case to help them collect the data from the environment and, of course, from the vessel. So this NetApp is mapped to the URLC type of slice. And yeah, this is the design choice due to the sensitivity of data on the location and speed of the vessel, which are further used by the other NetApps to derive decisions on the maneuvering, on the navigation and the planning of the trajectory and the determining the optimal speed of the vessel. So the important is that we have it received in the real time and that this is achieved with the highest possible reliability. This, of course, is regarding the practical deployment of this NetApp. We opted for a containerized deployment, and the whole logic of the NetApp is broken into different microservices, which are interconnected through open APIs, and also open APIs are exposed towards the other NetApps in the use case. This is the high-level overview of the NetApp architecture. On the right-hand side, on the left-hand side, we have vessel with publisher that is basically publishing data on the speed, location, and heading. And this data is being published to the subscriber on the NetApp platform. And here is basically our onboard data collection and interfacing with vessel NetApp, which is subscribed, and it receives the data through 5G URLC slice, and further processes this data in the data manager component, saves it and stores it in the data storage if needed, and then pushes it further to the other NetApps or other external NetApps developed by third-party experimenters. Also, possible scenario in this case. And not only publisher is enabling to these NetApps to consume the data from the VS8, but basically also the REST API to give them more flexibility in their software design choices. So both mechanisms through PubSub and REST API are available to share the data from the vessel. This slide shows the message sequence chart of the NetApp operations. And as I already explained while explaining the architecture, publisher running on the vessel is collecting, sending the data which is collected from the vessel. Subscriber on our NetApp is then using this data and processing it further in the data manager component, and further prepares data for storing and also for publishing on different kinds of topics. So we can expose here different topics if some NetApp wants to receive all bulk information about the speed, location, and heading, then it could subscribe to this type of topic. Or if some other NetApps require only the information about speed or location, they can instead subscribe only to those topics. The same applies through the REST API. Basically, all updates are being made each second for the data being collected from the vessel. And here, any external entity like any other NetApp can subscribe and get this data. This is one very simple but yet illustrative demo of how this NetApp works. I already explained it, but here you can see it visually. So this is basically the data coming from the publisher on the vessel. This subscriber on the VS8 NetApp is running in our premises on the NetApp platform. And then this data could be further exposed towards the other NetApps, like any generic NetApp that can be used here. My apologies for this interruption. Just a moment. Yeah, here it is. Back again. Okay. I'm coming basically to the end of the presentation. So here you can see you could see the previous slide, also the subscription on different types of topics, whether it is the whole topic with all kinds of data connected, but also to subscribe only to location, for example. To summarize my presentation here, I show how the NetApp, this particular NetApp, is placed in the overall 5G-based transport and logistics ecosystem. So if you want to develop a similar or this one, you can also need to, what you need is to have certain facility on the vessel side. Like there is a requirement on the GNSS device, and of course 5G device, to use 5G URLC slides to connect to the NetApp. And then regarding the 5G networking, we require a low latency and high reliable connection to onboard this kind of data from the vessel to the NetApp platform, so that other NetApps could make use of that kind of data. Here in the NetApp package, Jada already explained all the components in a very generic way that is same for any kind of NetApp. And here we just give examples of how these different parts of the NetApp package are basically filled in with the data from the onboard the data collection and interfacing NetApp. Here we show the descriptors and Docker images in the VNF package. Then here in the NetApp infrastructure, NetApp structure, like what are all the components that are present in the NetApp. Then here in the 5G mobile connection requirements, what you can also see from the NetApp blueprint is that the slice profile, the required one, is URLC, and this is the particular requirement on the reliability that we have. So basically in the very generic NetApp blueprint, we can specify these details to know what are the requirements from the network to achieve this operation that I've been talking about. And of course, the different kinds of 5G network and service related KPIs that are related to this NetApp, open API documentation for different interfaces like device specific and public interface that we developed for this NetApp, and different test cases that we are currently doing and performing within the VITAL-5G project. Regarding the next steps, so as you can see, we have this NetApp developed and deployed. An early drop version is already available. But what needs to be done is, of course, to integrate this NetApp with the other NetApps in our use case and to improve their operation by giving them access to the data collected from the vessel. And of course, what else needs to be done is to do the measurements and testings over the 5G deployment, because so far we have access to the 4G, and currently in this year we will have the overall 5G infrastructure ready so that the same tasks can be repeated and used instead of 4G. And of course, the idea by the end of this project is really to evaluate the impact of 5G and this NetApp concept on the operations and the port aspects. That's all from my side. Thank you very much for your attention. If you have any questions, we'll see them in the chat box. But if later on you have any questions, don't hesitate to send it to my email, which is on this slide. Thank you very much.
Thank you, Nina. Very good presentation indeed. Alex, the floor is yours. Alex, sorry, you are muted.
Now you hear me?
Yeah, I can hear you perfectly. Yeah.
Okay, thank you. So I hope you all see the screen. So thank you for still being here. After Jada's general presentation and Nina's description of vertical specific NetApp, now it's time for a vertical agnostic NetApp, which is a distributed sensor data ingestion, fusion, and automation. This is the agenda of the presentation. So as Nina, we will first describe the use case where the use of this NetApp is efficient, and then features and architecture of the NetApp, how data is collected, the data processing and the AI/ML mechanism, the technologies that are used in the NetApp, an example of a service that is offered in the use case using the NetApp composition, the blueprint, and the conclusions. So this is the use case that we have envisioned in VITAL-5G. It's called 5G connectivity and data-enabled assisted navigation using IoT sensing and video cameras. And it's taking place in a river port on the Danube in the city of Galaţi in the eastern part of Romania. It's the second use case of the project, and it's let's say it's illustrated in the following picture, where let's say we have a 5G network that supports connectivity as the ships are being close to the shore, and there are several services that are enabled. One of them is assisted navigation, for instance, where we have this cloud-based 3D map rendering that continuously processes the videos and the data and informs the assisted navigation systems. There are some KPIs that are, let's say, targeted, which you can see here, vertical and oriented and network KPIs, but also business and service KPIs. So the port of Galaţi has large logistics costs and has let's say a large number of dangerous navigation events. And by using the VITAL-5G enabled NetApps within its premises, there is this target of decrease by 15 and respectively 20% in these KPIs. This is examples of hardware that are being used on the ships. So there are pretty specific hardware, so not let's say mainstream sensors, so specific sensors that require some degree of adaptation in order to get data and to send it to a vertical agnostic NetApp. So basically, this vertical agnostic NetApp is also relying on a vertical specific NetApp, which is not the focus of this presentation, that we will briefly go through. And after studying this use case, taking into account the requirements from the port authorities, we have, let's say, graphed this use case 2 network requirements. It is similar to the graph in use case 1. We have also a need for high availability and high reliability. However, there is also let's say a higher need for capacity as compared to use case 1. And of course, there are the facility requirements, the end devices that we have seen, and examples of network requirements that are needed. And especially there is a need for higher throughput for several full HD video streams that are being used in the vessel. There are several, again, trial scenarios. This is an example where there is a difficult area in a river navigation. So basically, there is this need to prevent accidents in shallow water. So we need to use precise positioning sensors. We need to use depth sensors in order to circumvent the difficult areas, right? So this is an example experiment. We record the measured values of the depths, and we record the images that are captured by the cameras on board the ship. They are transmitted, and the specific information that is captured from this data collection is sent for the machine learning module in the NetApp that is used to predict the possibility of an accident. So from this, we go to the description of the virtual agnostic network application. Again, it is called distributed sensor data ingestion, fusion, and automation. Basically, it relies heavily on collecting data or raw data from the testbed. And then we have, let's say, the second part, which is the data ingestion, the imputation of missing data, the fusion of the data, the machine learning modeling, and outputs that are consumed by potential different other applications. So basically, what is specific here is that this functionality of data ingestion fusion is supported for distributed data sources. So you can see here on the left side the different possible sources of data that are being considered. Okay. So these are some features of the NetApp. It's a lot of text here, and basically it's what we have seen in the picture. So ingesting the data, transforming the data sets, send the data for other NetApps, and of course the post-processing of information, filtering, aggregation, and ranging for advanced analytics. And finally, appropriate APIs for other internal components or possibly third parties that can use the information from the NetApp. So this is an architecture of the NetApp, let's say a component-based architecture. So parts of these components are already in the VITAL-5G platform GitLab as an early drop. So the testbed and the data collection endpoints they are already there. And well, it more or less corresponds to the flow that you have seen before, and we will briefly describe each module. So the data collection is basically relies on a vertical specific NetApp for the ship in the Galaţi port. Of course, the core of the data processing, which is flow consisting of an MQTT protocol used for data transfer between sensors in the testbed, Node-RED, it is used for data processing, and InfluxDB as a database for storing time series, and from there onto the machine learning part, and possibly a Grafana engine for visualizing data. This can be applied to any type of data processing. However, it needs to be adapted for the specific sensors in the Galaţi port. So this is an example of a specific depth sensor that is, let's say, quite old, or not old, quite yes, ancient protocol, RS-385. It's heavily used in this. So this is just an example of the difficulties that are still in the part of sensor processing. Of course, these are overcome, and we process the data, and we manage to send it to the MQTT. This is, let's say, a more general description in which different devices are sent to our BEA MQTT broker, and we, using a specific adapter that we have developed within the company, are placing the data inside the time series database. And from there on, of course, this is if you are familiar, Grafana is naturally interoperates with InfluxDB, but also from InfluxDB, the data can go also to other engines that can process the data. And yeah, This is an example of a Node-RED flow that is we are using for data acquisition from a telemetry server, and that's serves different sensors and are sending them to the MQTT broker. And this is an example where we already have some results from a sensor that is used to measure water depth, and just for a visual representation, we can see here the data that is coming from such a sensor type. But this we went a little bit quicker through this because it's let's say vertical specific. From the data collection, we go to the data fusion module, which has a number of capabilities. So its main purpose is to perform a logical transformation of data that can be further used by other components. So what we saw before in the flow, imputation of missing values, time-space correlation, different types of transformation of unstructured data sets to structured and so on. The purpose is to have this data transformed, fused in a specific format that is sent to the machine learning module. All right, either when training the model or when applying the transformation. Now, the machine learning module is, let's say, can also be broken down into several components. It has unsupervised, both unsupervised and supervised modeling submodules. It has an auto-tune engine, which supports multiple modeling approaches and takes care of achieving the optimal hyperparameter tuning. And finally, a machine learning registry, which should store the best modeling approach. So within this module, we have mechanisms that ensure optimal machine learning model approaches to be used for the advanced analytics supported by this NetApp. Finally, we have a data persistence layer, which is actually a distributed data lake, which allows storing different, both structured and unstructured data. So we can have many, such as raw data, KPIs, the transformations of the raw data, the imputed data sets, the fused data, the machine learning modeling results. So if you can see, basically all these components have some connection to the data persistence layer. So at each point, we can have that data coming from such a component within this data persistence layer. And finally, this layer is also, or this component, sorry, this component is also responsible for exposing data through APIs, either to a dashboard, which could be Grafana or something else, or the components, and or third-party applications. This is an example of the NetApp of a service. It's the accurate electronic navigation maps creation, in which we see how the VA, the vertical agnostic, which is coded VA2 in the project, is using the vertical specific, which is coded VS9 in the project. So basically, the vertical specific NetApp is in charge of the data collection, sending the data through the 5G network. Whereas in the virtual agnostic, we take the data and we process it. And for instance, an example is to determine a safe distance estimation for this navigation map and send back to the vessel this information. We have a number of technologies that we are using when developing this NetApp. We have mentioned some of them, so InfluxDB, Node-RED, but there are also others, such as Apache Kafka or Apache HDFS, Hive, Airflow, MLflow, and so on. All of them are open source, so we envision that the entire network application is open source and can be reused by interested parties, and each technology has its own purpose, and this is used in this the functioning of this network application. Just like Nina mentioned before, this is an example of the blueprint of the NetApp and what is let's say what is needed. So on the vessel side, we need the sensors and the URLLC and EMBB slices because we need low latency and highly reliable network connection, but we also need high throughput for the video cameras. So these are relevant, the latency and the reliability are relevant for avoiding collisions and sending the emergency messages to the vessels. And of course, as input for other NetApps that, for instance, can perform predictive maintenance and AI ML-based diagnostics. So in the right side, you can see an example of the VA2 NetApp blueprint in which we outlined the infrastructure metrics, so the reliability, the latency, and the data rate that could be necessary in the deployment of such a network application. So finally, as a conclusion, this NetApp depends on on a vertical specific NetApp, but is also used as input for other NetApps within the same use case. We haven't yet deployed the sensors in on site. So starting this month, we are preparing to collect some data from the site over the 5G network. The IML mechanisms are still under development since they also depend on the availability of data. And after that, of course, there are the others components to be developed, open API-based interface, and finally testing, measuring of service and network APIs, and finalizing the NetApp. So thank you for the attention. This has been, the VA2 is jointly developed by BEA and our partners from Intelligence. And if there are any questions, feel free to write in the email, and then we can properly reply. Thank you.
Thank you, Alex. Are there any questions for the presenters? Of course, the presentation will be afterwards released on the YouTube channel of VITAL-5G project, and any kind of questions that you might have, please feel free to contact the presenter Jada, Nina, and Alex. If there are no questions, then I would like to thank everyone that joined today, especially many thanks to the presenters for their excellent presentations, and thank you again, and all of you have a nice afternoon. Bye.
Thank you. Bye-bye.
Thank you. Bye.
Thank you. Bye.
Thank you. Bye.
Goodbye. Thank you.
Okay,
Bye, everyone. Thank you.
Bye-bye.